everybody. Here, iPhone mic. Whiteboard I got from a medical student. And trusty dry erase pen. Today, we are going to talk about the nature of space-time. And I am going to attempt to show a different way of looking at space-time that may help explain gravity. I would like as much feedback as possible on this idea. First, we have to look at what is space-time. Okay, we have problem. I'll start out simply. Now, normally we would look at something like this as an x, y, z graph that we can use to make something as simple as a cube, where you have the height, width, length, simple, right? So, but we know that time is also a dimension. Time supposedly adheres to many of the rules that are spatial dimensions that we can't perceive, are bound by. Einstein did a lot of great work to try and prove this. But our brains are not hardwired to perceive this particularly well. So we're going to combine two dimensions and add a time, and then add a time dimension. So x and z are now being referred to on the same vector, and this dimension has now become time. Our box now is going to be y, z, and x, and t, where we could put these, where now we can add values to create a real piece of space-time with emphasis on the time. So this would be 1 meter by 1 meter by 1 meter, because remember there are now two values on this one vector. There's two dimensions being represented by there. I know that doesn't make sense. You can't picture it with your mind, with your brain, anything like that. What's important to remember here is that none of these spatial values are ever going to change in this experiment. And secondly, that astrophysicists and cosmologists use this all the time. And then this is now 1 second. This is called a fourth order tensor. It's a piece of space and time where we can see the time. Okay? What we see now is that this box has a volume if you include time as a dimension. 1 meter by 1 meter by 1 meter by 1 second. All with me? Okay. I'm going to redraw that here really quick. X, Y, Z, T. Sorry, this was X, Z, Y. With our box, this measurement is called 1 tenth. 1 meter by 1 meter by 1 meter by 1 second. And this is a very important measurement that we're going to use throughout this example. Now, what about the universe? So, the timeline, we're talking about time as a dimension. So let's go over time real quick. What we think of time today started at the Big Bang and will continue until, well, scientists are basically debating that. Current winner is cold entropic death of the universe, where our particles are all scattered evenly throughout time. Doesn't matter. We'll call it end, just for simplicity's sake. Now, we have our 1 meter by 1 meter by 1 meter column, specific piece of space-time. This is going to, relatively speaking, this is going to change with the size of the universe changing. But for this thought experiment, we can think of it as somewhat stable. So here is 1 meter by 1 meter by 1 meter. This is a cube of spatial time that's been compressed into a flat surface. Going for, I don't know, 20 billion years. Now, so let's say this is 10 billion, 13. We're right here, about 13 billion years old. Okay. Now, if we take a cross-section of this, this is composed of seconds, minutes, hours, whatever you want. But if we take a cross-section of 1 second of this, we have our tenth. Now, let's say we have a second space-time column, 1 meter by 1 meter by 1 meter, that is adjacent. And we also have an adjacent tenant from this space-time meter. My drawing was horrible, but imagine both of these are the same size boxes, 1 meter by 1 meter by 1 meter by 1 second, and they're right next to each other. Now, due to a crazy gravitational mass object effect, like let's say for 1 second, a particle with the mass of a small black hole appears. And for this experiment, relativistically speaking, of these two adjacent columns, only one was affected, not the other. What actually happens is one is affected less than the other or more than the other. So this is simplifying it, but ultimately it just helps us clarify how the process works. It doesn't alter any of the mechanics. So black hole has a lot of matter, and that has a relativistic effect. So for that 1 second, let's say the relativistic effect on this column is that speed moves time moves at 1/2 speed. That means, from a time universal perspective, the volume of this space-time has now increased. And we know this by comparing the two. Third, 1 meter to the third by 1 second, whereas this is 1 meter to the third by 1 second. However, this local time, once again Einstein, the concept of local versus global, or in this case comparative times, this 1 second has now taken up the same space as 2 seconds of non-affected, non-relativistic spacetime, right? Well, now, from a spacetime perspective, you are effectively looking at this as a volume problem. So, if this is a volume problem, what gets really interesting is when you turn a volume problem into a pressure problem. So, let's try and make this example really, 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 really easy. So, we have our one 4-dimensional tenant, that is, where there is no relativity effect. Space, our 3D space, represented on this top portion, where our 3D space is 1 meter by 1 meter, 2 dimensions being shared on one vector, for the time being, by 1 meter by 1 second. No relativity effect, just idling by. Now we are going to have the sister tenant over here that does have a relativity effect, as we showed. We're just blowing this all out. So 3D space right here, completely unaffected by relativity. Space does not get bigger or smaller when you have a relativistic effect. Our hypothetically convenient black hole, which we are using to demonstrate this effect. Now, from what we know about space and time, along its time axis, close to a large mass object, it will elongate. In this particular instance, we're assuming that the space-time relativistic effect is going to be double, because double is really easy to understand. Okay? So this dimension, so t is now times 2, which means that it's 2. But one thing Einstein proved, local time is always local. So for me, in here, enjoying myself a big frosty glass of lemonade. It takes me 1 second, 1/10 worth of time to drink this lemonade, drink really fast, to the outside world. It will appear to have taken 2 seconds. Excuse my drawing, this is supposed to be a square. And this is also another tenant, so another 1 meter by 1 meter, by 1 meter by 1 second piece of space-time. It's in fact the same, 3 of these dimensions are the same, one of them has changed. The same as you could have the facade for a storefront be the same while changing everything else, all the walls inside of it, all the space inside of it. That would be totally different. The space-time has changed, the facade has stayed the same. And in the 1 second it took me to drink a lemonade, to an outside observer who's, let's see, I got a little telescope here. Same guy right here, this little telescope. It will have taken 2 seconds. So it's 1 second plus 1 second. So comparatively, the time dimension has now doubled. If the time dimension is now doubled, you have the same amount of space-time in twice as much 4-dimensional space. This inherently creates a high-pressure, low-pressure system. This is the high-pressure system, the unaffected, the ones that have not been affected by relativity. This is the low-pressure system. Space-time, the same amount of space-time now occupies twice as much space. This effect everywhere else in the universe, thermodynamics, fluid dynamics, pretty much anything you can name, the tendency when you have going from a low entropy to a high entropy situation, you have the same amount of stuff in a low volume and the same amount of stuff in a high volume, is to have pressure build up from high to low. High pressure to low pressure. There's half as much. If you consider this a 4-dimensional object as opposed to a 3-dimensional object, there's half as much space-time pressure pushing back. Now, this is very, very interesting when you think of it in terms of gravity, because now you have pressure systems in space-time. Pressure systems potentially a way of describing some of the mechanics of gravity. This is something I would like to explore further. I think this is an interesting concept. Thank you. Bye-bye.